Right, so differentiating hyperbolic functions. So here are the results. We've got to differentiate sinh, it differentiates to cosh, which differentiates to sinh, and tang, which differentiates to sec squared. Now these results are very similar to your trigonometric results, except they are all positive. So they are exactly the same, and apart from the derivative for cosh being positive. So how do we show that cosh indeed differentiates to sinh? Well, we're going to use the exponential definition of cosh. So remember, cosh x is equal to e to the power of x plus e to the power of minus x over 2. So to differentiate cosh means to find the derivative of e to the power of x plus e to the power of minus x over 2. So this will be, well, e to the power of x over 2 goes to e to the power of x over 2, and e to the power of minus x over 2 goes to minus e to the power of minus x over 2, which is e to the power of x minus e to the power of minus x over 2, which is sinh x shown. Okay, now you might have to apply the chain rule. So cosh 3x is going to go to, well, cosh goes to sinh. If it's 3x, you'll have just 3 sinh 3x. Done. Differentiate x squared cosh 4x. So of course we can use the product rule. So let u is x be x squared, v cosh 4x. Let's differentiate u to get 2x, and v dash is going to go to 4 sinh 4x. So the differentiated answer of the product x squared cosh 4x. So remember, it's vu dash plus uv dash that we need to use. So these two times together give me 2x cosh 4x plus x squared times 4 is 4x squared sinh 4x. Okay, now we're going to find what the second derivative of a cosh 3x plus b sinh 3x is, and then hopefully it will end up being 9y. So let's differentiate it once. So a is just a multiple of cosh 3x. So cosh 3x goes to 3 sinh 3x. So it will go to 3a sinh 3x. b sinh 3x goes to 3b cosh 3x. Let's differentiate it again. So sinh goes to 3 cosh, multiplied by 3a, you'll have 9a cosh 3x, and cosh goes to 3 sinh, multiplied by 3, you get 9b sinh 3x. If you factorize 9 out, you will have a cosh 3x add b sinh 3x, which is our function y. So that's equal to 9y. Again, shown or proven. Okay, you also have the 3 results. So differentiating hyperbolic inverse hyperbolic functions. These are again in the formula booklet, they're available, but you need to be able to apply it, and obviously we're going to have a go at this right now. So over here we've got the product x r cosh x. So that's the product. U dash is 1 and V dash is going to be R cosh differentiated. By the way, you could be asked to differentiate it from scratch, so hopefully there will be an example like this and we can apply it. Let's just use the product rule. So VU dash plus UV dash. Okay, so VU dash for dy dx will be 1 times r cosh, so r cosh x, plus uv dash, so it's x times 1 over x squared. You have x times 1 goes on the numerator, and there's the answer. Okay, example 21, we have to use we have to differentiate y equals r cosh x all squared, and then hopefully we will square that result and rearrange it to make it look like this. So let's start by finding dy dx. So if we use the chain rule, so we're going to use y equals to u squared and u equals to r cosh x. So that gives me dy du is 2u, which is 2r cosh x, and du dx is going to be 1 over square root of x squared minus 1. So dy dx is going to be dy du multiplied by du dx. So that gives me dy du, which is 2r cosh x multiplied by 1 over square root of x squared minus 1. So dy dx, we can square it because we are aiming to get the result with a squared, is going to be equal to 4r cosh x all squared, and then if you square the square root, you get x squared minus 1. So if you look very carefully, r cosh x is y, well, all squared is y, and then we can multiply through the denominator to obtain x squared minus 1 dy dx squared is equal to 4 times y. Okay, so again, shown or proven. Let's have a look at the final example, example 22 of that section before exercise 6D. So first of all, here is a good example of how you're going to show from scratch that r sinh differentiates to 1 over 1 plus x squared. So we're going to say let y be r sinh x, and before you applied r sinh, you had sinh y equals x. We can differentiate x with respect to y, so dx dy is equal to cosh y. So now we want to go back to x's, so cosh y is equal to, well, we're not going to go to exponential definitions. What we're going to do is use the identity. So remember, the identities are, you will have a cosh squared y minus sinh squared y equals 1. So cosh y is equal to square root of 1 plus sinh squared y. There you go. Okay, so let's have a go at popping it over here. So cosh y is equal to square root of 1 plus sinh squared y, which is 1 plus x squared. So that was dx dy is equal to, so let's flip it, dy dx is equal to 1 over 1 plus x squared. Part B, find the first two non-zero terms of the series expansion of r sinh x. So let's have a look at part B. So the series expansion is looking, so we're talking about Maclaurin. It's going to be the first term is f of 0. The second term is f dash of 0x. The third term is f double dash of 0x squared over 2 factorial, etc., etc. Okay, so we need to find these derivatives and see if any of these will disappear. So f of x, let's say y is our f of x. So this is going to be r sinh x. So f of 0 is going to be equal to 0. So r sinh goes through the origin. So then you've got f dash of x. So this is the result that differentiates to 1 over square root of x squared plus 1, which is x squared plus 1 to the power of minus a half. So f dash of 0, if I put 0 plus 1 is 1 to the power of minus a half is 1. F double dash of x, so let's apply the chain rule. That will go to 2x times by minus a half. So let's just do it. So minus a half x squared plus 1 to the power of minus 3 over 2 multiplied by 2x. So you're going to multiply the 2 together. You've got minus x times x squared plus 1 to the power of minus 3 over 2. So f double dash of x, if I put 0 into that, you have 0 times something that will disappear. So let's go for the third derivative. So here we're going to use the product rule. So this is u and this is v. So using the product rule, u is equal to minus x, so u dash is minus 1. V is equal to x squared plus 1 to the power of minus 3 over 2. So v dash is going to be minus 3 over 2 multiplied by x squared plus 1 to the power of minus 5 over 2, and then multiplied by 2x. So this one is going to be 2 and 2 will cancel, minus 3x, x squared plus 1 to the power of minus 5 over 2. So using the product rule, you will have vu dash, so it's minus x squared plus 1 power minus 3 over 2 plus these two times together. So minus and minus will go to plus 3x squared, x squared plus 1 to the power minus 5 over 2. So the third derivative at 0, this part will go to 0 plus 1 to the power of minus 3 over 2, so you have minus 1 left, and this one will go to 0. So let's have a look at the fourth derivative. So the fourth derivative, now how many terms do we need? Oh, okay, we don't need any more. So if you want to do the fourth one, do it for practice. So find the first two non-zero terms. So we're going to stop at the third one, so which is going to be x cubed term over 3 factorial. So y is going to be f of 0 is 0, f dash of 0 is 1, so plus 1 times x, f double dash is going to be 0, and then you're going to have minus x cubed over 3 factorial. So y is equal to x minus x cubed over 6. Okay, so moving on to part C, they are giving you a general form for the series expansion of R sinh, and it's given by R sinh is equal to sigma R starting from 0 up to infinity, and then you've got this lovely expression in the bracket with lots of exponentials and powers going on, and then you've got the x to the power of 2n plus 1 over 2n plus 1. So the fact that x has got the power of 2n plus 1, that tells you that you can only generate odd powers of x. So find in the simplest form the coefficient of x to the power of 5. So if you think about it, when you put 0 into this expression instead of n, you're going to get the power of 1. I'm just trying to think that should be n here if they're using n in this expression. So that is what it should be. Right, so if they, that would be generating the coefficient or the term involving x. If you put 1 into this, you'll have 2 times 1. So if n is equal to 1, then you will generate x to the power of 2 times 1 plus 1. So it's going to be x cubed term. So we have to use n equals 2, because then you've got x to the power of 2 times 2 plus 1, because that will be x to the power of 5 term, and that's what we want to do. We want to find the coefficient of the x to the power of 5 term. So using n equal to 2, we are going to have this term being minus 1 to the power of 2, and then 2 times 2 factorial, and then 2 to the power of 2 times 2, which is 4, and then 2 factorial all squared, and then it will be x to the power of 5, because when you sub 2 in there you will have 5, and then you will have 5 on the bottom. So use the calculator, or I haven't got the calculator handy, so that's going to be 1 times 4 factorial, and 4 factorial is going to be 1 times 2 times 3 times 4 over 2 to the power of 4, and then 2 squared. So 2 squared is 4, so we can cancel that with this, and that 2 will cancel with this. You will have 2 cubed left, and you still have x to the power of 5 over 5. So it's 1 times 3 on the top, which is 3, and it's 8 times 5, which is 40, x to the power of 5. So the coefficient is 3 over 40. So just to mention one more thing, it says our sinh of x is equal to sigma n starting from 0 up to infinity. That means the sum of all the terms. Okay, so that's pretty obvious. I didn't mention it though. Okay, so part D, we use the approximation up to and including the term in x to the power 5. Oh, see, so that's why they ask us to use this, so we can generate the x to the power 5 term, because we have generated through differentiation the other two terms, which should be approximately equal to x minus x cubed over 6. So f of x is equal to x minus x cubed over 6, well, approximately equal to, and then you've got plus 3 over 40 x to the power of 5 term. Obviously you could generate further terms, but we haven't been asked to do that. Okay, so we are going to use this to find our sinh of 0.5. So we're going to let x be equal to 0.5. So this will be 0.5 minus 0.5 cubed over 6 plus 3 over 40 multiplied by 0.5 to the power of 5. So use your calculator to work out the answer, and the answer should be 0.48151. Didn't ask us to give it to any specific number of decimal places, so that is probably enough. Okay, and then calculate the percentage error in using this approximation. So obviously you could write all the digits that the calculator is displaying, but you will have them on the calculator. Now the percentage error is simply, you've got to take your approximation. So in general, it's going to be your approximation minus the true value over the true value multiplied by 100%. So if this answer is going to, if you do approximation minus the true value, the answer is positive, then the approximation is bigger, clearly, so it's going to be an overestimate, so it's still an error. Okay, if it's negative, then it's underestimate. So approximated answer is 0.48151. The true answer is R sinh 0.5, which you could use your natural log or the calculator, because the calculator will have option for using that for calculating it, multiplied by 100%, and the answer should be 0.06223 decimal place, which is hardly any percentage error if the percentage starts at the second decimal place. So it's a really, really accurate formula. So now you can go ahead and do exercise 6D.